Hello everyone, I am 𝗔𝗀𝘁 from Seoul National University presenting Elsa, hardware-software co-design for efficient, lightweight, self-attention mechanism in neural networks. This work is done with my colleagues at Seoul National University and my advisor Jae Lee. The first two authors contributed equally to this work. Transformer-based models are achieving state-of-the-art performance on various natural language processing tasks such as question answering, translation, language modeling, and so on. Recently, transformer-based models are also being adopted for computer vision tasks such as image classification and object detection as well. The key mechanism of the transformer-based models is its new primitive called self-attention mechanism. This primitive is in charge of identifying relations within input entities and enables transformer-based models to effectively handle sequential data. For example, as shown in the right figures, the self-attention mechanism enables transformer models to identify the noun that a pronoun refers to. One common characteristic of the transformer-based models is their large model size. Some of the recent transformer-based models, such as OpenAI GPT-3, have hundreds of billions of parameters, which also comes with a high computational cost. And self-attention mechanism accounts for a large portion of computation in transformer models. For example, our measurements showed that the self-attention accounts for more than 30% of the total runtime in popular transformer-based models. As shown on the right side of the figure, this portion becomes even larger when the input sequence length is increased. Here, I'm going to explain how the self-attention mechanism works. The self-attention mechanism gets a query matrix composed of multiple query vectors, and a key matrix composed of multiple key vectors, and a value matrix composed of value vectors that correspond to each key vector. The goal of self-attention mechanism is to find relevant key vectors to a given query vector and returning the weighted sum of value vectors corresponding to relevant key vectors. The self-attention mechanism has three steps. Let's look at how it works for the first query that corresponds to the first row of the query matrix. First, it computes the dot product value of each row in the key matrix and the query. The result of dot product value is called attention score. Second, it proceeds softmax normalization on the attention scores, which produces softmax normalized attention score. The softmax function computes the exponent of each attention score and normalizes it with the sum of exponents. This process assigns large weights to the keys with high attention scores and low weights to the keys with relatively low attention scores. After normalization, the sum of all softmax normalized attention scores for a given query is 1. Third, using the softmax normalized attention score as weights, the self-attention mechanism computes the weighted sum of value vectors. In this slide, the first key has the highest softmax normalized attention score, and thus the final output vector is very similar to the first key's value vector. As you can see from the previous slide, self-attention is a series of dense matrix operations, but it is also a content-based search. After computing attention scores with dot product operations, those scores are normalized with the softmax function. So as a result of this normalization, most scores, excluding the few largest scores, are mapped to almost zero, and they barely impact the final output. As you can see in the slide, most scores, excluding the largest score of 10.9, are mapped to 0 or near 0 values. Based on this characteristic, our work presents a way to approximate the self-attention mechanism. By finding out the set of candidates that are likely to be relevant to the query with little computation, we can avoid processing irrelevant keys, and also we can reduce the amount of computation. We find that this approximation results in significant improvements in performance and energy efficiency. The presented approximation is a way to reduce the computation for self-attention mechanism. However, we find that such an approximation does not always lead to speed up on conventional hardware such as GPUs. This is because GPUs are better optimized for full similarity computation, which is dot product. To fully exploit the benefit from the reduced computation requirement of the approximate self-attention mechanism, we need specialized hardware. Thus, we introduced Elsa, hardware-software co-designed for efficient, lightweight, self-attention mechanism. We present novel approximation algorithm and a specialized hardware so that Elsa achieves significant reduction in runtime as well as energy spent on the self-attention mechanism. As I mentioned earlier, not all keys impact the final output equally, so it barely impacts the final output even if we skip the operations for the keys with low attention scores. However, computing the attention score for each key and query pair requires d multiply and add operation. Thus, it takes total n² d operations for all n² pairs. So what we propose here is to map each query and key vector to a binary vector in a way that preserves its similarity of attention score to reduce the number of operations. And using these binary representations, Elsa proposes a novel way to approximate attention scores in a lightweight and efficient manner. Now let's dive into more details about how Elsa approximates the attention score. The dot product of two vectors is the multiplication of the norms of each vector and the cosine value of the angle between two vectors. Once again, self-attention is finding relevant keys to a given query Q, so for a given query, the norm of the query is the same for all keys. As a result, we can find relevant keys without knowing the norm of the query vector, as you can see in the equation. The key idea of Elsa's approximation scheme is that we can efficiently compute approximate cosine values using the binary hashing method. For convenience, let's assume two-dimensional vector space. As you can see in the slide, we can think of three vectors, x1, x2, x3 in the vector space. Then, to map each vector into k-dimensional binary space, we create k random vectors. In the figure, we assume k is 4, and 4 random unit vectors are illustrated in the slide. Then, for each vector, x1, x2, and x3, we compute the hash value. The hash value is the concatenation of sign values of the dot product between vector x and a random vector. Geometrically, a sign of the dot product between vector x and a random vector is equivalent to inspecting which side vector x belongs to among two partitions defined by each random vector. Let's look at how we can get hash value for vector x1. Vector x1 is on the minus side of random vector v1, so its sign value is 0. Similarly, vector x1 is on the plus side of random vector v2, so its sign value is 1. And vector x1 is on the plus side of random vector v3, so it's 1. And vector x1 is on the minus side of random vector v4, so it's 0. We can easily get hash value for vector x2 and x3 in similar way. Then, we can easily compute the angular distance between two vectors using these binary vectors. In order to compute the angular distance between two vectors, we need to first compute the Hamming distance between the corresponding binary vectors and then multiply pi over k. For instance, in order to approximate the angular distance between vector x1 and x2, we compute the Hamming distance between those two binary vectors, which is 1, and then multiply pi over 4 to obtain the estimated angular distance pi over 4. And for the angular distance between vector x2 and x3, we compute the Hamming distance between those two, which is 4, and then again multiply pi over 4. The estimated angular distance here is pi, and you can see that the angle between vector x2 and x3 is almost pi in the figure too. Similarly, we can get the approximate angular distance between vector x3 and x1. The principle of this method is that each hash vector divides a two-dimensional space, and there is a high probability of two vectors having smaller angular distance when they belong to the same splits in many cases. There exist several literatures that prove that this method provides an unbiased estimate of angular distance. Here, I summarize the process of obtaining the approximate attention scores for each vector. First, we compute the hash values for keys and a query, and also the vector norm of each key. Second, we compute approximate attention scores for each key using the equation shown in the slide. Originally, self-attention required demultiply and add operations, but now it only requires bitwise XOR and lookup operation on lookup tables where each entry stores pre-computed cosine values for all possible Hamming distances. This computation can be performed very efficiently with the specialized hardware, which will be introduced briefly. Then, in candidate selection process, we filter out potentially irrelevant keys whose approximate attention score is below a pre-trained threshold T. Now, let's look into candidate selection process in more detail. In an ideal case, it would be the best if we sort all approximate attention scores and select top scoring keys. But the main issue here is that sorting is expensive in hardware, and sorting can only happen after computing all keys' estimated score is done. Thus, in Elsa, we select keys whose estimated score exceeds a certain threshold. In this way, we do not have to do expensive sort, and we do not have to wait until all keys' approximate score computation is done, since filtering can happen right away after a key's score estimation is done. Now, a question may arise. How do we find the right threshold for all of the NN layers or sublayers which easily exceed hundreds? The answer is we learn from the training data. Here, we show how Elsa trains the threshold for each sublayer in the model automatically. First, a user sets a hyperparameter P for accuracy performance trade-off. And here, n is the number of keys, and given this P and n, our goal is to only consider the set of keys whose softmax normalized attention score exceeds P over n. For example, if P is set to 2 and the number of entities is 200, we want to only consider keys whose softmax normalized attention score exceeds 0.01 and ignore all keys with normalized scores below it. With this mechanism, a high P indicates aggressive approximation and a low P implies conservative approximation. The challenge here is to find the raw attention score that will generate the normalized attention score P over n. For this purpose, we utilize the training set to find the average of raw attention score for keys whose normalized attention score just exceeds P over n. For example, from below case where n is 4 and P is 1, we learned that the threshold for the raw attention score is 0.86, since this is the least score whose normalized attention score is larger than P over n, which is 0.25 here. We repeat this process for multiple cases and take the average to derive the filtering threshold for the raw attention score. Now it is the hardware part. The Elsa specialized hardware operates in two phases, pre-processing phase and execution phase. During the pre-processing phase, the specialized cache computation unit computes hashes for all keys and then stores them in the key hash memory. The details about efficient hash computation and its hardware are presented in the paper. Once the pre-processing phase completes, the execution phase starts. The execution phase consists of 3 steps, and the first step is to compute the query hash. As in the pre-processing phase, the hash computation unit computes the hash for the query and then stores it in the unchipped buffer. Then, the next step is candidate selection and attention computation. Here, multiple candidate selection units compute the approximate similarity between keys and a query in parallel, and then filter out keys achieving low similarity with the queries. The keys that are not filtered out are then passed to the attention computation modules. The attention computation modules receive the ID of the keys that are not filtered out by the candidate selection modules and then perform attention computation with those keys. In particular, the attention computation module computes partial attention output for each key and accumulates it in the buffer at the end. Finally, once the attention computation finishes, the outcome is then divided by sum of exponents for the normalization purpose, and this generates the final outcome for the self-attention operation. Our hardware is carefully pipelined to maximize the self-attention throughput. The hardware performs computation for multiple query vectors in parallel using the pipeline parallelism, and each step of the execution phase is also further pipelined to maximize the throughput. The details for the pipelining are explained in section 4 of the paper. Now let's look at the evaluation result. First, we show the impact of the approximation to the model accuracy. In this figure, P is our hyperparameter for accuracy and performance trade-off, and paper provides more details about this parameter. The purple line graph in the figure shows the model accuracy across varying P, and the overlaid bar graph shows the portion of selected candidates across varying P. Overall, the figure shows that our mechanism is effective in filtering out unnecessary keys with minimum accuracy degradation. For example, Elsa approximate self-attention mechanism achieves less than 1% accuracy metric degradation while inspecting only 1/3 of the keys. The figure compares the self-attention throughput of 12 Elsa accelerators and a single NVIDIA V100 GPU having similar theoretical peak flops. The figure shows that Elsa achieves 8 to 46 times speedup over GPU without the approximation, and the approximation adds even further speedup on top of that. Our presented Elsa accelerators requires about 15 square millimeters area for 12 units, and then the peak power consumptions for those 12 units is 11.47 watts, which is much smaller than that of V100 GPU. The top left figure shows the energy efficiency comparison of Elsa accelerators with GPU. Elsa accelerators achieve 2 to 3 orders of magnitude energy efficiency over conventional GPU. The top right figure shows the energy breakdown of Elsa accelerators, and this figure shows that Elsa consumes very little extra energy for performing approximate candidate selection. Thank you for listening to our talk. Please refer to the full paper for more details. Thank you.